On Tuesday, June 16, 2026, a 15-year-old boy in Magnolia, Texas, walked toward the edge of a flooded suburban retention pond and vanished beneath a quiet sheet of brown water. 300 miles to the west, in Bandera County, northwest of San Antonio, another life was claimed by a few feet of moving water across a road that looked, for one fatal second, like it could be crossed. Hold these two deaths in your mind because they expose a profound systemic paradox. At the moment of these fatalities, the atmospheric system responsible was not a hurricane. It was not even officially a tropical storm. Its maximum sustained winds peaked at 45 miles per hour, a velocity weaker than an ordinary summer thunderstorm gust, a force you could easily survive standing in your front yard. Yet, it had already bypassed the structural defenses of the state of Texas. This anomaly officially received its name on June 17, 2026, Tropical Storm Arthur. It arrived as the first named storm of the Atlantic hurricane season, organizing before the season was even 3 weeks old. In mid-June, the Atlantic basin is climatologically quiet. The deep tropical engine, the warm core, the African wave train, the low wind shear typically does not assemble until much later in the summer. June storms, when they occur, are traditionally disorganized, homegrown Gulf of Mexico nuisances. On paper, Arthur was designated as exactly that, a short-lived 45-mile-per-hour cluster projected by the National Hurricane Center to rapidly dissipate. But the data reveals a completely inverted reality. The classification chased the catastrophe. It did not lead it. Long before the National Hurricane Center issued its first designation of potential tropical cyclone 1 on the morning of June 16, this unmapped precursor system had been systematically dismantling regional infrastructure. South of the border, in northeastern Mexico, the system had already devastated Veracruz, triggering dozens of landslides and inundating over a dozen municipalities. In Coahuila, over 5 inches of rain fell in a mere 2 hours, flooding the city of Piedras Negras and damaging 70 to 80% of the road network in another major municipality. As the system crossed into Texas, stalled against an inland frontal boundary, refusing to move, and began pumping a continuous column of tropical moisture northward. In Waco, nearly 3 inches of water fell in hours. Austin's Camp Mabry set a daily rainfall record for June 15, shattering a marker that had stood since 1964. Over 100 low water crossings across the Austin area were instantly submerged, trapping drivers, forcing the evacuation of an entire RV park, and leaving residents stranded in trees awaiting emergency rescue. This is the central paradox of the Arthur anomaly. The system did not follow the established sequence of tropical genesis. Traditionally, we are conditioned to expect a storm to form over open ocean, strengthen, make landfall, and then distribute its precipitation. Arthur did the exact opposite. It rained, then it formed, and only then was it named, all while its primary moisture field was already anchored deep inland. The standard metrics of meteorological warning, the categories, the wind speeds, the cones of uncertainty, failed to register the true scale of the crisis because they were measuring the wrong hazard. To understand how a system too weak to knock over a patio umbrella can paralyze entire watersheds, we must dismantle our conventional understanding of atmospheric structures. We must analyze this storm not as a wind machine, but as a slow-moving, highly efficient aquatic conveyor belt. The actual danger lies in the mechanics of its origin, a rare transcontinental convergence that stitched together the dying breath of an eastern Pacific storm, Tropical Storm Christina, with an Atlantic tropical wave over the anomalously warm waters of the Bay of Campeche. This dual ocean genealogy created an atmospheric system that was saturated with water before it ever developed a defined circulation. When wind shear stripped the storm of its vertical structure, it did not diminish the threat. It merely dispersed it, turning a compact storm into a massive, disorganized shield of tropical moisture. Now, as this waterlogged remnant slides eastward at a mere 9 miles per hour, barely faster than a casual bicycle ride, it is moving over coastal terrain already saturated by its own precursor rains, triggering a feedback loop known in geophysical literature as the brown ocean effect. This brings us to the fundamental systemic threshold we must confront. When the National Hurricane Center inevitably downgrades this system to a post-tropical remnant and files its final advisory, When the public radar graphics disappear and the news cycle moves on, does the danger actually recede? Or is the most lethal phase of a waterlogged storm the silent, unmonitored phase that comes after everyone stops watching? To understand how Arthur survives inland, we must examine the interface between the atmosphere and the terrestrial surface. In a typical scenario, a tropical system loses its primary energy source upon landfall and decays. Arthur, however, operates over a coastal zone primed by its own precursor precipitation. This is the brown ocean effect, a documented thermodynamic process where saturated waterlogged soils mimic the thermal properties of a warm sea, evaporating moisture back into the boundary layer to sustain the system's precipitation engine. Simultaneously, upper-level wind shear continues to tear at the storm's low-level circulation. Rather than neutralizing the system, this structural disruption acts like a strong crosswind on a campfire, tilting the vertical core and displacing the convective bands. The wind threat collapses, but the precipitation field expands, transforming Arthur into a massive, slow-moving moisture shield encompassing 16 million people across the Deep South. This brings us to the mathematical reality of a stalled system, the arithmetic of slow. Total precipitation at any geographic point is determined by rainfall rate multiplied by duration. Operating at a forward speed of only 9 miles per hour, Arthur's rate-to-duration ratio escalates exponentially. When individual convective cells align along a single trajectory, a process known as training, successive bands of intense rain pass over the exact same watershed like rail cars on a track. While widespread totals average 5 to 10 inches, these training bands produce localized bullseyes of 15 to 20 inches. At the coast, this freshwater volume collides with a second physical barrier, storm surge. Driven by the counterclockwise rotation of the system, a 2 to 4 foot surge accumulates along the right front quadrant, pushing Gulf waters inland and acting as a hydraulic dam. In low-lying, pump-dependent landscapes like southern Louisiana, this compound flooding forces rainwater to back up into the streets, overriding municipal drainage systems. This physical reality directly dismantles the superficial narratives that inevitably populate the public sphere. The first false frame is that of artificial weather modification, often attributing such systems to high-frequency antenna arrays like HARP. The fundamental thermodynamic equations of the atmosphere render this claim impossible. The heat energy released by a mature tropical system dwarfs the entire electrical generating capacity of human civilization by a factor of hundreds. We cannot engineer these systems. We can barely measure them. The second false frame is that Arthur represents an entirely unprecedented climate apocalypse. In reality, the physical laws governing this event are well defined. Sea surface temperatures in the Gulf were running over 1 full degree Celsius above the long-term baseline, with the loop current supplying deep oceanic heat. Under the Clausius-Clapeyron relationship, every single degree Celsius of atmospheric warming increases its water-holding capacity by approximately 7%. Thus, a warmer Gulf does not guarantee a higher quantity of storms. Indeed, seasonal forecasts remain restrained due to El Niño-induced wind shear, but it systematically raises the ceiling on the maximum potential precipitation of any single system that does form. The third false frame, that a 45-mile-per-hour storm is a minor event, is refuted by history and physics. In 2017, Hurricane Harvey's winds rapidly collapsed after landfall, yet the stalled system dropped over 60 inches of rain, a mass so immense that geophysicists documented the Earth's crust sinking by 2 centimeters under the weight. Similarly, the nameless Louisiana flood of 2016, which was never classified as a tropical storm, dropped over 20 inches of rain and caused billions of dollars in damage. The warning threshold is not a wind scale. As Arthur is reclassified to a post-tropical low and the official advisory cycle terminates, the public instinctively relaxes, equating reclassification with dissipation. This semantic shift is the final, most dangerous trap. The structural decay of the wind field does not diminish the moisture column. As the remnant shield pushes into Mississippi, Alabama, and Georgia, the danger decouples from the designated track, threatening saturated watersheds long after the headlines have declared the storm to be over. This spatial decoupling of damage from the storm's track is the ultimate systemic hazard. While major urban centers like Houston were largely spared the worst-case scenario through a combination of favorable track alignment and proactive water management, the peripheral risk remains acute. In Brazoria County, water managers deliberately lowered drainage reservoirs, and the San Jacinto River Authority made preemptive releases from Lake Conroe to absorb the incoming volume. This demonstrates that mitigation can successfully alter the local damage function, but it also creates a false sense of regional security. The sparing of a highly engineered metropolitan center tells us nothing about the vulnerability of the unmonitored rural watersheds and small communities downstream. The water does not negotiate with political boundaries or infrastructure deficits. This structural vulnerability is particularly severe across the rural Deep South, where the ground state has recently swung from extreme drought to sudden saturation. Throughout the preceding spring, much of Louisiana, Mississippi, and Alabama experienced a prolonged moisture deficit. Under these conditions, drought-baked soils undergo a physical compaction, forming a hardened crust that acts like a solid barrier rather than an absorbent sponge. The initial rainfall cannot infiltrate the deep soil layer and instead converts immediately into rapid surface runoff. As subsequent bands of moisture train over these hardened surfaces, the water accumulates in the shallow valleys and local creek systems with extreme velocity, turning small, unmonitored channels into violent, high-volume torrents beyond the freshwater flooding. The thermodynamics of this decomposing system introduce a secondary, highly localized hazard: embedded tornadoes. As Arthur's low-level moisture plume collides with a cooler frontal boundary sliding south out of Arkansas and Mississippi, the vertical wind profile begins to warp. The rapid change in wind speed and direction with height, known as low-level wind shear, initiates rotation within the convective cells. These are not the massive, highly visible supercells of the Great Plains. These are brief, low-topped, rain-wrapped tornadoes that spin up in minutes. Because they are structurally obscured by torrential rain and frequently occur at night, they bypass conventional visual warning networks, requiring immediate, non-visual defensive actions. This brings us to the core human variable in geophysical crises: the administrative battle against public complacency and the false alarm tax. Across the Gulf Coast, public officials must constantly balance probabilistic risk against the political and social cost of aggressive warnings. When the governor of Texas placed 101 counties under a state of emergency, or when parish officials in southeast Louisiana issued mandatory evacuations, they did so in direct opposition to the national narrative framing Arthur as a minor nuisance. Every time an evacuation is ordered and the worst-case scenario fails to materialize, a fraction of public trust is eroded. The population slowly conditions itself to ignore future warnings, treating a survival rate probability as a guarantee of safety. This psychological friction is where the final trap of the Arthur anomaly closes. The physical laws governing water, gravity, and terrain operate independently of human nomenclature. The atmosphere does not require a category designation to transport energy, nor does the rain require a name to inundate a home. The true baseline of risk is not determined by the wind scale of the National Hurricane Center, but by the thermodynamic load of a warming ocean and the inevitable mechanical limits of our coastal geography. Until our collective warning models shift from wind-centric categories to water-centric risk profiles, we will continue to find ourselves unprepared for the silent, patient hazard that remains long after the wind has died and the headlines have turned away. We must now evaluate the final physical trajectory of this event and confront the underlying systemic reality. As Arthur's primary moisture field transitions across the central Gulf Coast into the eastern states of Mississippi, Alabama, Georgia, and the Florida Panhandle, the physical components of the system continue to disperse. This brings us back to the speculative upper bound, the absolute ceiling of what a moisture-saturated, low-wind atmospheric system can achieve when all environmental variables align in the worst possible way. In this low-probability, high-consequence scenario, the forward speed of the post-tropical remnant slows to a complete stall. The warm Gulf of Mexico continues to feed a continuous stream of water vapor into the lower atmosphere, while an upper-level block holds the system stationary over a highly populated infrastructure corridor. when a system of this magnitude stalls over a region with limited geographic gradient. The results are mathematically predictable. The drainage networks of the Deep South, designed for historical precipitation baselines, reach their carrying capacity within hours. Once the soil reaches complete saturation, the transition from absorption to runoff is instantaneous. In this state, there is no buffer left in the system. Every gallon of water that falls from the sky must move laterally across the landscape. In flat, low-lying coastal plains, this water does not rush away. It creeps sideways, expanding horizontally into residential neighborhoods, business districts, and agricultural zones that have no historical record of flooding. This is where the human factor collides with the hard limits of engineering. In many of these areas, local zoning laws and flood maps are based on outdated historical baselines that assume a stable climate. When a 50-year or 100-year flood threshold is crossed by a system that the public was told had weakened, the psychological defense mechanisms of the community break down. Residents who chose to remain in their homes because they were outside the official flood zones find themselves surrounded by rising water with no means of egress. The failure is not one of municipal response, but of systemic imagination. The system was designed to withstand a specific historically bounded class of disaster, and it is being forced to process a thermodynamic load that exceeds those parameters. We must also deconstruct the final superficial interpretation of this season's quiet start. While seasonal forecasters predicted a near-normal to below-normal storm count due to El Niño-induced wind shear, this metric is frequently misunderstood by the public as an indicator of safety. The total number of named storms in a season is a measure of quantity, not intensity or local impact. A quiet season with only 9 to 13 named storms can still produce a generational disaster if a single system stalls over a vulnerable watershed. The thermodynamics of the Gulf, where sea surface temperatures have run more than a full degree Celsius above the long-term baseline, remain the primary driver of precipitation potential. The seasonal wind shear may prevent these storms from organizing into high-wind hurricanes, but it does nothing to decrease the absolute volume of water vapor carried by the atmosphere. Ultimately, the lesson of Tropical Storm Arthur is a lesson in structural limits and cognitive bias. The 15-year-old boy in Magnolia and the driver in Bandera County were not killed by a meteorological category. They were killed by water behaving according to the laws of physics. Water seeks the lowest point, it accumulates where it is blocked, and it moves with a force that human infrastructure cannot indefinitely contain. When we look at the radar images of a decaying post-tropical low, we are not looking at a storm that is fading away. We are looking at a system that has shed its wind profile to reveal its true, most lethal component. The water is patient, the terrain is fixed, and the structural limits of our defensive systems have been clearly mapped. The question is no longer when the next major hurricane will make landfall, but how much longer we can afford to ignore the silent, waterlogged systems that are already rewriting the rules of survival along our coasts. To grasp the absolute boundary conditions of our geophysical safety net, we must recognize that the Arthur anomaly is not a malfunction of the natural system, but its logical optimization. When the Gulf Ocean temperatures consistently exceed historical averages, the physical response of the atmosphere is non-negotiable. It is a rigid thermodynamic equation that plays out in real time across our coastal plains. The system operates on an energy budget where human intervention is functionally zero. Our engineering, from the suburban retention ponds of Houston to the massive pump stations of New Orleans, was designed around a historical baseline that is rapidly dissolving. The structural limits of these systems are being reached not by the violent, dramatic shear of wind, but by the quiet, cumulative load of water. This structural deficit is compounded by a profound cognitive gap in how we calculate risk. We have built a modern warning apparatus that categorizes threats almost exclusively by wind speed, using the category scale as a universal proxy for danger. This is a severe conceptual error. By prioritizing a single, easily measured hazard, wind, we systematically underprepare for the primary engine of mortality in tropical systems, freshwater inundation. A 45-mile-per-hour storm like Arthur is dismissed as a nuisance. Yet its water volume is structurally identical to the late-stage, devastating phases of a major hurricane. The water does not care about our meteorological boundaries or administrative classifications. It operates strictly on the laws of fluid dynamics, gravity, and topography. When we tell a community that a storm is weakening or has become post-tropical, we are using a vocabulary that is technically accurate for wind, but dangerous and misleading for water. The true metric of danger is the thermal load of the ocean beneath. The Gulf of Mexico, running more than a full degree Celsius above its climate baseline, is a massive thermal reservoir. Under the Clausius-Clapeyron relationship, this elevated temperature loads the troposphere with a massive moisture surplus. This is the fuel that drove Arthur, and it is the fuel that will remain in place through the peak of the season. Even if wind shear prevents the formation of classic photogenic Category 5 hurricanes, the threat of extreme localized water bombs remains historically high. The seasonal forecast of a quiet or below average year in terms of storm count is a dangerous distraction. A quiet season does not mean a safe season. It merely means fewer rolls of highly loaded dice. It only takes one slow-moving, poorly organized system to park over a vulnerable watershed and trigger a multi-billion-dollar catastrophe. This is the ultimate sobering reality we must confront as the remnant moisture of Arthur continues its eastward crawl. From the flat bayous of Louisiana to the hard, drought-baked soils of Mississippi and Alabama, the vulnerability is systemic. The tragedy is that the hardest hits will likely occur in places that were never in the official crosshairs, far from where the center made landfall, and long after the official warnings have been terminated. This is the signature of the modern waterlogged storm, damage that decouples from the track, occurring in the dark, under a sky that no longer has a name. The 15-year-old boy in Magnolia and the driver in Bandera County were not victims of a freak accident. They were the predictable casualties of a system running at its absolute physical limits. As the remaining rain bands wring themselves out across the Deep South over the next 48 hours, the machine will continue to function precisely as physics dictates. The water will continue to rise, the exits will continue to close, and the silent, patient hazard will wait for those who believe the danger is past, simply because the wind has gone quiet.